up the basics of probability. So we're doing statistical inference, and the most important thing for generative modeling is maximum likelihood estimate. So we have seen this example in the last class, and I hope everything is clear because this is more or less the most useful thing. Of course, the way we use the parameter and all this depends how we use them. But so the way we took theta over 3 because we knew that theta is the number of blue balls. So if theta is 3, then obviously 3 over 3 is a surety that that it's a blue ball, and so on. So these are the modeling assumptions that you may do. So essentially, what was the idea? Idea was that we want to learn the distribution of the red and blue ball in the bag. Okay, this is the most fundamental concept that you have to learn. Okay, and then everything else in the world is a distribution. Okay, how the pixels are arranged is a distribution, but then if it's a cat, then it's some kind of distribution. If it's a dog, then it's some other kind of distribution. Okay, I want to be fair with both the cat and dog lovers. So, but text, if you're going to write certain type of text, then it follows certain type of distributions and so on. Okay, what follows next after you have written certain text, that it will also be decided by the probability next likelihood of the next word, given that what you have seen. So basically, this is the most fundamental thing. You will see this again and again where we write maximum likelihood. So everything should be okay. And what happened here? It's a data-based learning, because I picked some samples, and based on the sample, I learned the distribution. So this is the parametric distribution by theta, parameterized by theta. Just like I'm fitting a neural network in data, but here we are fitting this data in a distribution. And what is the use? After I know the distribution, then essentially I know the distribution of the balls in the bag, and this will help me emulate the behavior of how the balls will be generated if I start sampling. Okay, so once you build this, then you can ask your friend, and you can say, look, this is how if you pull the balls, this is how the likelihood of the blue ball or the red ball going to be. That's very similar to learning images, because we can ask the same thing. Okay, how should I pull the pixels so that they look like cat? Okay, that's very fundamental thing. So this is more or less what we did in the last class, and obviously there were some assumptions, and you can say why should I use independence, right? So this is joint probability, right? So you've seen joint probability of two variables x, y, but then now we are talking about 4 random variables and joint distribution for that. Okay, so joint distributions is like the intersection of these events happening. So x1 taking certain value and x2 taking certain value, and so on. Okay, and then so in general, joint is not necessarily product of the marginals. We know that. Okay, so joint is not necessarily product of the marginals. This is a very big assumptions that we are doing here, and it may go wrong. In fact, it does go wrong for images. Okay, I will give you an intuition. We will build on this quite a lot, and we will go ahead with autoregressive models, normalizing flows, and so on. But for images, you could have done like that. Given a grayscale images, these are the pixels values. So if it's a grayscale, and let us say these colors take only black or white. So with this black-white pixels, you can generate certain shape, right? So certain image of a cat or something. So you can think of that like that, and these are all the pixels that you have. And then you are asking of what is the joint probability distribution of these pixels that resemble a cat, and so on. Okay, and from maths point of view, if we want to go fit the distribution, then it is greatly simplified if we assume that this is product of the marginal, which essentially means that joint being equal to product of the individual PDF means it's independence assumptions. Obviously, we are assuming that xi's are independent, and this simplifies quite a lot. And this is the prediction function that we have, the parameter of the distribution that we have. And now all we have to do is that, since this is a probability, we want to maximize the probability. So which value of theta will maximize the output that we observe. Okay, that's essentially so that's why we have to maximize. Unlike the neural network, we have loss functions and the error in prediction via minus the error in the expected output. Here it's something else. Here it's like for the given data, our prediction should be the highest possible for the given data. So it's a maximum likelihood problem, and it's an optimization problem. It's maximized over theta, and since theta was discrete, then we saw that we could have just put those explicit values of theta rather than using the traditional optimizer where we take the gradient. In fact, we will we can do that as well at some point, but for this it's just that the way we assume things, it's a discrete, so just put on those values and see for which values it's maximized. Again, I have not fixed the error in my slide here. Again, this was supposed to be like 0.9 something, and then so for 2 basically theta equals to 2 it was supposed is the max, and that's it. So theta is equal to 2, it's the max, and if we go back, then our distribution, the parameter distribution is this. We have found theta. So basically you have only missing thing in your distribution was theta. So now it's a Bernoulli 2/3. So the distribution is like Bernoulli 2/3. Now you sample from here. Once you have learned this distribution, now all you have to do is sample. Again, how you sample would be interesting problem. Given a distribution, how you sample. Okay. So we may want to make our life easier by sampling from a distribution that is very easy. Easy meaning uniform distributions. If I ask you to pick a sample from, let's say, 1 to 100, then the typical way that you will pick, it will be mostly uniform. Okay, you will guess. Okay, 51. Okay, 99. So this is easier for me. So sampling from uniform is easier for me rather than Bernoulli. So we need one more ingredient, something called push-forward distribution. So from a distribution that I know it's easier to sample from, and that will translate to distribution from where I can sample. Okay, so we will come back to that. So there are 2 things now, maximum likelihood estimate, and once you learn that distribution, this distribution itself, sampling from there. Okay, what is the process? So we will see that a very simple hint is look at the CDF. CDF lies between 0 and 1 because it's cumulative probability, and CDF lies between 0 and 1. You sample from here, you track the inverse of the CDF. So those who could already see that far, that's your hint, but I will make things precise a bit later. So more or less this is what we have. So we can formalize the definition. So we had this example. So what we are interested in is, given a set of samples, in this case x1 to xn, we want to look at the likelihood function, which is nothing but the joint probability distribution, and it is parameterized by theta, obviously. So this theta may not be a scalar value, it may be a vector, depending on what type of distribution you're trying to fit. If it's a normal distribution, then it's a 2 parameter, and if it's Bernoulli, then it's 1 parameter. So it depends which type. So this is a very generic definition of a likelihood function. But then we may also want to, and if it's a continuous, then remember in discrete we use P or PMF. And if it's continuous, then we use F, PDF. Okay, so this is just a change of notation, and then in some cases it's easier to look into the log likelihood rather than the likelihood. Okay, why? Because if you look into normal distribution, then you have exponential to the something. So if you take the log, exponential goes away, and you have a simpler expression to maximize. Now we assume that maximizing likelihood should be at the same point where the log likelihood got maximized. So there is a little bit of issue that may arise from the optimization point of view, because we have taken a log of the L. Okay, this is a log of the likelihood. So what is so our original problem was to maximize likelihood with theta, but what if I take the log? Maximizing the log may happen at some other theta than the actual theta that I was looking for. So a simpler intuition would be that if your L likelihood is let us say so in which cases it will not disturb, right? So what about log, right? Log, is it a monotonic function or non-monotonic? It is monotonic, right? So if you compose with a monotonic function, then in many cases it won't get affected. The minima or the maxima where this L will the maxima where the L will be maximized won't be affected where log L will be maximized. Okay, so so in general it's actually won't suffer by maximizing the log, and it's much simpler. Okay, so I may do the first one, let us say so binomial 3 theta, and we have observed the samples 1, 3, 2, 2, and similarly you can try as an exercise exponential now. So exponential binomial has 2 entry, but the first entry is not you specify as 3, and the parameter is actually theta. So and the exponential is a single parameter distribution. So again, you have some observations from there, and you may try to write down the likelihood function. So if I write down the likelihood function for the binomial, it is we recall that the binomial distribution is given by this PDF. In this case, a binomial is like n comma p, but n is 3 here, so 3x, 3 choose x, and theta is the parameter that we want to know. So theta to the x, 1 minus theta 3 minus x. Okay, so so we can write down this is just a practice of writing down the likelihood. So we write down the likelihood in the binomial case, and in the binomial case we assume again the independence assumptions. So this is a product of the individual PDF. So 3x1 theta to the x1 1 minus theta to the 3 minus x1, and then multiply it with 3x2 theta x2 1 minus theta 3 minus x2. So if you combine all of them, 3, there are 4 of such 3, so it's 12 minus, and then take all this x1 plus x2 plus x3 x4 common, and then theta also has only x, so this gets added. So our likelihood function is for this data. So obviously our data that we collected is 1, 3, 2, 2. So this is our x1, x2, x3, x4, and we put it here. So basically it's only a function of theta. Okay, and as we know, we want to maximize the likelihood. So with respect to theta, this is an optimization problem with respect to theta. So we can do that, and just for formality, so this is likelihood function. How we write that, and this is very similar to the example that we did. It's just that now we have binomial instead of Bernoulli in the example, and then the maximum likelihood estimator is nothing but the theta that maximizes the likelihood. So just for formality, I have also included this definition in the slide. Now we go ahead for the same problem, binomial theta, where we wrote the likelihood, and it was just for your convenience maybe. Yeah, 27 theta to the 8 1 minus theta to the 4, right? So we took the derivative of that. We want to maximize. So the usual optimization method tells us that you take a derivative and equate to 0. Okay, and of course something may go wrong. As I said previously, some basic optimization method, not just basic, actually good amount of optimization method is also useful in machine learning. So things can go wrong because taking derivative and equating 0 could be maxima, minima, because gradient becoming flat can happen also at minima, at maxima, but we are looking for maxima. So you have to be a bit careful. But it so happens that if you do that, equate to 0, and then you indeed get theta to be 2 over 3, where it gets actually maximized. Okay, so so this is how maximum likelihood works. And as I said in the previous class, the likelihood function that you take is your choice. This is the inductive bias that you are assuming, because many distribution could fit a given data. It's like you are the one who are forcing it to fit. Okay, so when you are working with classification problem, regression problem, whatever problem, it's your choice of the neural network you are forcing it to learn, right? So this is the inductive bias that you impose. Which one is good one, which distribution is good one, it depends. Okay, if you have some additional information, like in the case of the bag, I knew that there are only 2 balls, red and blue. So it was a case of a binary. Bernoulli fits very well. Okay, so if some information is there about the range and all this, then obviously you get some idea about picking this PDF. Okay, so this is and our favorite normal distribution, or the Gaussian distribution. Okay, so this is what this is our friend that we will see again and again, and according to CLT, this will, in a big data setting, normal distribution will more or less approximate many other distributions. So that's why you keep seeing this Gaussians everywhere, Gaussian mixture model and whatever. Okay, because more or less it's good enough. Okay, most data start behaving like standard normal. Okay, so we can try maximum likelihood estimate, but as I said, because of the exponential, log would be very good in this case. So you don't want to see this e to the something going, and you want to maximize with this exponential term. So here in this case, the log will really simplify. It just becomes a, I believe, quadratic, I guess. So again, given a set of samples x1, x2, x3, xn, you will assume the independence. Again, maximum likelihood estimation you simplify by assuming that it's IID, but it's not necessarily the case that you have to simplify that, because the definition as such, you may want to write down this joint probability distribution in different ways, for example using chain rule. Okay, so we will see that shortly a little bit. So independence is just one possibility, and there are very fascinating ideas just on this, like one of the the autoregressive models, pixel RNN, CNN are more or less like this. Okay, so okay, I'm going back. So we can do exactly the same way that we did. We have the PDF. We will assume as a first step that they are IID. In fact, random sample, as I said, the definition itself includes that it's IID, but so then this PDF will split and so on. Okay, we take the log. So this is the actual calculation. So it's just a calculation. It's nothing to be kind of afraid of. It's just that now this is a joint probability distribution, right? With n normal random variable. So there is an explicit formula for that. I don't know if the TA did this previously. So this is like the n-dimensional Gaussian PDF you can think of. So this is the joint, or for a vector of random variables. So sometimes we can combine them and we call it a random vector by capital X. Okay? So it doesn't matter as long as you remember the formula that for n-dimensional there is a summation going on here, which you don't see in the usual case. And those two parameters for normal distributions, usually first one is for the mean and second one is for the variance. They do show up like this. So basically you have to memorize this. This is so important distribution that usually you memorize this. And then we prefer using log because obviously it kind of becomes quadratic and there is a log term there. So this is a little bit more than the single parameter case, because now you are supposed to maximize over two variable function, right? So this is maximize over xy, fxy. Okay. So basically this is an optimization problem. Now you are maximizing over two variables. Okay. So now there will be now instead of taking one derivative, now you have a gradient. You take a gradient because there are two variables. So gradient will be a vector of length 2. So basically the first component of the gradient is partial derivative with theta 1. And if we do that, then obviously we have to equate to the gradient to 0. So if we recall this, so this is gradient with xy, fxy. So this is del by del x fxy, del by del y fxy. And the usual process is like the gradient should vanish. Okay, so in the curve case, it's just that. So assuming that it's a curve, so it should vanish in along both the directions essentially. Okay, so the requirement for minima or maxima, actually it should be maxima. So you have to be a bit careful. So what we are looking for is something like that. So this is what we are supposed to do if it's a critical point, which we assume that also has a maxima, not necessarily minima. So we take gradient equate to 0. That's exactly what we did. Our variables are x1 and x2, theta 1 and theta 2, sorry, and partial derivative with theta 1. This is a simple function, as you can see here, taking derivative with partial derivative with theta 1. This is a constant that goes away, that goes away. So essentially you are left with this, and there is a minus with theta 1, minus becomes plus. So this is 1 over, and then there is, and this theta 2 gets cancelled because we are equating to 0. Not theta 2, not theta 2, because the 2 basically we throw away, but theta 2 we keep it. But I believe even theta 2 we will throw away because we will from the first one we will solve for theta 1. So what can you guess theta 1? Theta 1 is the usual sample mean, right? If I solve the first one, you can see that theta 2 goes away, assuming that the variance is not 0. Then essentially x1 theta 1 is 1 by n sum of xi, which was sample mean that we saw in the previous class. So sample mean is the approximation of the unbiased estimator of the true mean. In reality, we work with samples. That's why we are doing statistical estimation. Okay, so this parameter that we are looking for, theta 1, is sample mean, and similarly it will look like sample variance if we solve for theta 2 now. Okay, so we are supposed to solve for theta 2 as well. So if we solve, okay, you may verify this offline that theta 1 hat should come out to be sample mean, and theta 2 hat is coming out like sample variance. Okay, so the way sample variance we defined was x minus the mean, but mean because we only have data in hand, the mean is our sample mean. So this is not the true mean. Obviously we don't know the true mean of the data. We are only working with samples. So we put this theta 1 hat, and if you can recall, we had a slight adjustment, like -1 was the unbiased sample. This was the unbiased estimator of the of the variance, but it's okay. So even if you took n instead of n-1, it doesn't matter when n is large. So overall, this is what we get. The estimation of our θ1 will be nothing but the sample mean, and estimation of the θ2 will be our sample variance. Okay, and all this is being decided from the data. Okay, so given a set of data, I'm trying to fit a normal distribution, and I am assuming the IID, and if I do that, then if I can memorize this formula, then I can immediately know which distribution is going to fit. My distribution mean should be sample mean, so xi's are known, n is known, how many samples I took. I can immediately calculate this, I can immediately calculate this. I immediately have the distribution that I was looking for, and the only thing is to know how to sample from normal distribution. Again, I can make your life easier by this so-called push forward distribution, where I can say, let's say uniform distribution, you can sample, and I know a way to the way you sample from uniform, it will translate to how you sample from the normal. Okay? We need some kind of push forward distribution and so on. Okay, so so this was the important one. Some additional result that it may happen that as you are taking more and more samples, then what can you say about these maximum likelihood estimators? Okay, are they good? So these results say that yeah, they are good as long as if n tends to be going to infinity, then your estimator, p maximum likelihood estimator, the probability of that being away from the true quantity that you want to estimate, in this case is theta, that's going to be 0. So basically this result says that the way you use MLE estimates, as the data size grows bigger and bigger, you will approach the true estimator, and okay, and it becomes asymptotically unbiased as well. Okay, so there is an example that you can try. It's a very simple example, so you may try this. And you may try an example of where you took a geometric distribution. So we did Bernoulli, we did binomial, exponential was previously there, and you can try MLE estimate for geometric just for practice. You can also try this for uniform distribution, what could be the maximum likelihood estimator. So okay, so now let us come to the images, right? So the way we will do is that we will learn something, we will go back and say we will not completely solve it in one shot because we need context from time to time. It's a challenging course to teach because there are so many interconnections. So what I will do is that I will give you some initial intuition. You can think over this for 3-4 classes, and then I will come there after 3 classes, and then I will give you the full solution for that. But it needs a lot more context. So with what we know, let us try to figure out what could happen with images. Okay, so images, let us say in the simplest case we are looking at handwritten digit, and this is a grayscale image, not just grayscale image, pixels are just black or white. So it's like binary values are given. I'm not giving intensity values of these pixels, how much gray or something. No, it's completely black or not black, which is white. Okay, so this is our model. So this is our data, and x1, x2, xn are binary random variables. So this xi takes value 0 or 1, and which means that it's black or white in this case. Okay, as you can already see, for color images things get pretty high dimensional, right? But let us try to build an intuition just for the black and white. So first thing is how many possible images are there when we have this, right? So if there are, I believe there are n pixels. Okay, so let's say total n pixel. We can see them as long vector. So you can order them and see them as long vectors. There are n pixels, and each can take 0 or 1 value. Okay, so 2 times 2 times 2 times 2, n times. So there are 2 to the n. Okay, so that's pretty high, because you will see people working with 32 by 32. Okay, so this is 32 by 32 pixel. Basically it's a matrix of pixels, 32 rows and 32 columns, and so basically n is 32 squared. N is 32 squared, and the possibilities for the images that you can build with is like this. This is more than the number of atoms in the universe. Okay, so atoms in the universe are approximately 2 to the 80. Okay, so that's way more that we can handle. Okay, so the number of possible images itself. So this is already a very high dimensional problem. Okay, and with what we have learned, we want to see the joint probability. Obviously, joint probability of these pixels, because obviously they jointly describe an image, right? So the arrangement of x1, x2, xn jointly, the probability of those happening in certain way defines that it's a number that we want to recognize as a good number. Okay, so so this is what we want to know, and so as such, because it's a joint probability distribution, if you don't assume the independence assumption, then as such it should be described by 2 to the n parameters, because there are so many possibilities are there. Okay, so essentially if you don't approximate the joint probability distributions, then all possible values should be taken into account, and that can only be described by order 2 to the n. So obviously we will assume independence assumptions like we did in previous examples. So if we assume the independence assumption, then it gets simplified. The joint probability distribution now is written as a product of individual probability distributions. So with independence assumptions, how many parameters are now required? So to define one, let us say single parameter distribution, so this is p x1, so I will need one parameter, px2 I will need one parameter, pxn I need one parameter. So there are n parameters required. Okay, so does it work for images, right? Our original MLE estimates that we have seen, does it really work? Unfortunately it doesn't work. Okay, so if I fit this distribution for handwritten digits, okay, so for handwritten digits I will, this is our sample. Okay, so I did the sampling of these, okay, x1 x2 xn, okay, and then saw the distribution of these pixels, and then I did another one and another one and so on, and I tried to fit the distribution, and it turns out that I get something like this, which is not really close to the handwritten digit. Okay, it looks like some random thing. So if you try to use these independence assumptions, then unfortunately for images it's not that simple. Okay, images are complicated, they have local dependence. Okay, so you got to make a little bit more complicated model. Pure thinking of this pixel has nothing to do with this pixel is a very simplistic assumption for images, and that's why it's not working. Okay, so what do we do? Since we learn probability, we may apply chain rule. We may assume some form of ordering, although the initial ordering really doesn't matter, but we may I mean it may matter actually to some extent, but assume that we have some ordering, and rather than saying that it's product of the individual, now we write it as using the chain rule of probability. So px1, and then we write px2 given x1, then what is the probability of x3 given that x1 and x2 are seen, what is the probability of xn given that x1 x2, it should be x. Okay, so it's xn minus 1 is seen. Now what is the intuition behind chain rule? The intuition behind chain rule is that for images dependencies are required, okay, to make sense. So having seen these pixels, what is the probability of this pixel, right? Having seen these pixels and these pixels, what is the probability of these pixels? So there is a relation of, so if I write 9, then the way pixels are arranged one after the other have some meaning. Okay, so that's why we are looking at the conditional probability now. Pick any first pixel, that doesn't matter, but having seen the first pixel, what are the possibilities you are going to have? So starting from here, it could have been 9, it could have been 3, or here we don't know. Okay, so here at the same spot, my x1 was this guy, x1 is this guy. It has now few possibilities of 9, 3, or even 6. But as it sees more and more, so after it sees these many, then it will go away from 6. Then it has 3, 4 possibilities. It may go for 3 still. It may go for 9, and so on. So so this is forcing some kind of ordering, some neighbor relationship that is needed for images. So if we go with the chain rule, but if we go with the chain rule, the exact form, if we do that, then again we are dealing with 2 to the n, because for the first one it's okay that I need one parameter because it's a distribution px1, but for this it's a 2 parameter model because it depends on x1. So if x1 is 0, one possibility. If x1 is 1, then there is another possibility. So as if px2 x1 now needs, it's a 2 parameter model, okay, rather than 1 parameter model. So because it's conditioned on x1 takes 2 values. It's conditioned on x1 and x2. So now it's a 2 to the 2 parameter model because x1 takes 2 values, x2 takes 2 values, So you will need 4 parameters to precisely describe px3 given x1, x2, and so on. So if you add that, so px1 is 1 parameter model, px2, x1 is 2 parameter model, and this is 2 to the n minus 1, then you are still dealing with 2 to the n. This is because I went for the exact form. So here again, now you may think of what could be done. Okay, so should you really look at very long window of all the pixels that you have seen so far, or is it enough that you truncate and see only some of them? A very simplistic assumption is Markovian, where you expect that the next thing that I'm going to do only depends on my current state. Okay, that's the Markov property. So that would be like the very crude one, but that's one possibility. Okay, so if I assume like that xi depends only on xi minus 1, then if you will see that I truncated quite a lot. Okay, so px1 and then x2 given x1, until here there is no approximation, but then x3 I am looking at only x2. So I am saying that having seen x2, I am forgetting x1. That's the Markov property. So I am forgetting x1. I am looking at what is my current pixel value and what could be my next pixel prediction x3. So this is simplistic. Okay, so there is a typo here. This p n minus 1, it should be xn minus 1. So with this parameter needed for px1 is 1, parameter needed for px2, x1 is 2, all 2. Okay, so basically 2 n minus 1 and 2 of n minus 1 and then plus 1. Okay, so minus 2 plus 1 is 1, so it's 2n minus 1 total. Okay, so number of parameters, total number of parameters required in this case is 2n minus 1, which is order n. Okay, so which is still way less compared to 2 to the n. So you may go with this model, but then in this framework you may now you may tinker a little bit and maybe explore a window of 2 rather than 1. So it depends what you want to do, how much approximation you want. In fact, whole of this machine learning and all this area is all about how do you really understand the problem, how can you approximate, okay, what is a good approximation, bounds and all those. So this is something one has to see based on the applications you are dealing with. So what we have seen so far is that we are essentially trying to fit a probability distribution, and for few problems maximum likelihood estimate is more or less okay. But for cases where we have images, then it's not that simple, because images have some kind of more inherent local dependencies. Even for simple grayscale images, maximum likelihood estimate is treating each pixel as independent is not a good idea. If you are tossing a coin n times, we know more or less that tossing a coin n times are independent. Tossing one coin has nothing to do with another one. These are not like that. Images are not like that. If you do that, you will always get random set of pixels, and they will never look like set of handwritten digits. Okay, so more needs to be done here. Okay, even to predict, even to build this distribution functions, you want to maybe fit this distribution functions, right? So you want to fit each of these. They are parameterized neural networks. Not neural network. Okay, maybe I already gave some hint. So the most important thing that has happened, that drives more or less everything nowadays is neural network. So at some point, even to estimate a probability distribution, I may need the power of neural network. Okay, given a set of pixels, can you predict me the probability distribution for the next set of pixels? So that's where we will put a sub-neural like that. That will be our extension. But we will see that a bit later. In fact, I will go with some neural network introduction. There are some students who are very new, so I will go with a neural network introduction very quickly. But that will cover like more or less, it take the whole class, and then we will come back. And there is a lot to do here, but we will leave it here. You may think by your own what could be next set of possibilities, but I will leave it here. Okay. So now I will go to very quickly about Bayesian inference. We have seen so far the classical inference. Also for Bayesian inference, I'm just going to give you very basic minimum. Okay, we will develop as if we require. Teaching everything upfront doesn't help. Okay, so the whole idea about Bayesian inference is to draw inferences about unknown variable x by observing a related random variable y, but that is like more or less the inference problem. The unknown variable is modeled as random variable x with prior. This is the important part. Now you are given a prior distribution, okay, and you are going to cheat a little bit. Okay, you will use this prior distribution and then find out even a better estimate compared to the classical inference, which is not using any prior distribution. So that's more or less the idea. So after observing the value of the random variable y, we find the posterior distribution is something that you want to find. Okay, so so the posterior distribution is usually found using Bayes formula. So if you have seen the Bayes formula, then it relates x given y to y given x. Okay, that's the idea behind. So that's more or less how we are going to estimate the PMF using the Bayes rule, given that we are given some prior on x. Okay, so these are same formula. It's just that if x is a continuous random variable, then we change p by f. That's all. Otherwise, more or less everything remains the same. There are cases, if you have seen probability, done some problems on probability, sometimes you have hard time finding py, but then you can make use of law of total probability and expand this using that. So that's so in this case also, just like maximum likelihood estimate, and now we may want to do a similar estimate, okay, using the Bayes rule, but then in this case we want to maximize the posterior estimation in this case, and if we do that, then it's called map estimate. Okay, compared to the MLE estimate, now you have the map estimate where you are maximizing the posterior distribution. So I guess it will be more useful when we will do some actual use of this. So if you look at the Bayes rule, the denominator has nothing to do with when we are maximizing this, because it's a maximization over x. So then we can get rid of the denominator completely, and it's only about maximizing this f of y given x, and then if we compare it with the maximum likelihood estimate, the maximum likelihood estimate will be this, but then map estimate just differs from the fact that it brings in the prior distribution as well. Okay, so actually for our case we will be dealing with maximum likelihood estimate only. There will be one or two cases where we will come back, revise this again. I am not interested in spending too much time right now on the map estimate, because we don't need that much. We will need a little bit, but not that much. So for the moment, you keep this in mind, that in the map estimate there is this additional factor of the prior distribution somehow shows up, but then in the MLE estimate we have already seen with many examples, you want to maximize the likelihood given the samples we have seen and so on. So that will be all, and then there is an example also. I will try to post this example, and then you may try to find out the map estimate and so on. So okay, so I will kind of stop here with the statistical estimate, and then I will go to the basics of neural network. Okay, so I will discuss basics of neural network because that will show up from time to time. So some of you may be already aware of this, but then it may be a good revision anyway. I borrow some of the slides and pictures from the original source. It's a very highly recommended source from CMU deep learning course. Much of the power of machine learning and all this news that you see on Twitter, LinkedIn, and all the new everywhere on the magazines and YouTube and so on, it's mostly powered by neural networks. Okay, at the end of the day, somewhere inside there is a neural network. If you just remove the neural network, you go back to 1950 or 60. Okay, that's how important neural networks are. So speech recognition is now a very easy thing now. Okay, language translations are done on daily basis now. Okay, image segmentation recognition is a very typical task now, so typical that now it's not even sure that you should work on these things now, because industry has completely taken over these things. They are always doing better than academia. Yeah, recognition of like which of the car model and all this. Okay, so these are pretty standard. In fact, these were done already like 3-4 years ago, so these are already old. Behind these things also, AlphaGo and all this, there is a neural network somewhere that's taking all the kind of the giving all the power, the prediction power. Okay, it looks at all the set of states where your pieces are, the actions you are going to take, and it somehow predicts your optimal moves or policies that you are going to take as a next step. So again, without neural network, it's nothing really. I mean, that's how important they are. image captioning. Okay, so sometimes Facebook can caption an image very easily. Okay, if you allow it to do so. So the first step in understanding neural network is something called perceptron. Perceptron is the basic element, the atom or something like that of a neural network. So it was proposed somewhere around 1956. Okay, the basic idea, but it got refined in later on. So the way initially it was defined was like very kind of sometimes even philosophical. So we don't want to kind of spend too much time on that. We may go quickly into the maths. So as I said, there is a neural network behind more or less everything. Yeah, so again, as I said, most neural networks start with this philosophical introduction that we are thinkers. We are thinkers because we have a brain. We have a brain, and then it is with neural network, it has the ability to learn, solve problems, recognize, create, and so on. Then initial one was theory of cognitions. Like they were basically trying to understand. Okay, so basically how you learn. Okay, so some initial theories were like law of conjugacy, law of contiguity, law of frequency, law of similarity. If you see similar things again and again, you are good in recognizing. Sometimes if you see opposite things, you are good in recognizing. Sometimes if you see things quickly enough, you remember. So there were these initial proposals of what could be the way learning process happens. And then there were ideas behind so-called connectionism. And if they look at brain, then there are a set of neurons and they are connected like that. But then within there, if you see closely, then there are neurons. Okay, and these neurons somehow processes information incoming one, and then what to send next to the next neuron, and then overall it makes sense of whatever. Like I mean, basically all the senses basically more or less will be based on neuron. Okay, so it's not just in head. I guess throughout we have like kind of sensory organs. So initial ones, as I said, will be very like various ways people were thinking about that, putting edges between neurons and thinking about how. One of the things that was very puzzling, so to say, because if you look into the modern day CPUs, computers, then you have processors, you have program and data. Okay, so you have explicit idea about memory, right? But even those things were very confusing in the beginning. Like where is the memory, right? I remember something in my mind, but where is it stored? Like only thing I see are neurons here and there, but where exactly is the data, right? So our thinking of data being separate and programs look very different. So these were very puzzling initially. In fact, yeah, even now it may look a little bit puzzling because these large language models are nothing but just neurons with weights, and these weights are everywhere distributed. Okay, so you cannot say there is explicitly separate memory somewhere. Okay, the weights and activations, processing, all are kind of combined. Okay, so it's a little bit different than the von Neumann model of the modern CPU that we have. So there were ideas behind initial ideas behind what could be the components of this thinking machine, okay, or distributed machine. There may be processing units, activation functions, things like that. But these initial ideas were very crucial to get to exactly what perceptron would be. Okay, so the neuron model is like this. I'm not an expert on this, but this is more or less how it looks like. There are some receptors. It takes some certain signals, but again, the signals are like kind of analog signal and not necessarily the digital signal that we are used to. Okay, so I mean the way we have things implemented in the digital computer, like analog. Obviously, we have analog circuits and so on, but the way we run the codes and all this are kind of digital. So, but here it's even more intricate because there are like chemical reactions going on, change of potential, and all this somehow is the information that can be processed. So it's quite complicated. Even we don't know like what else is going on here. Okay, there's all chemical reactions going on, and some processing happens, and then you sense. Not just sense, like you can do so many things. Okay, so this is still a big mystery. That how exactly the brain really works, because it's a mystery because there is physics, chemistry, so many things involved here. So you may play around with some small prototype ideas. What could be an excitatory signal? What could be an inhibition of the signal? And based on those combinations, you may say, okay, this is what is going to be the prediction. I'm a bit hand wavy because of the time, but there were Similar ideas behind emulating the Boolean gates, sensory things. So how can you build a heat sensation devices and so on. Okay, so but what really was a breakthrough was the so-called Hebbian learning, where for more or less the first time they thought about learnable weights. Okay, so these are the weights, and this is actually similar to the gradient descent. Again, I'm not going into detail of all this, but the idea here is that with the observations we have, with the samples we have, can we update the weight. So this is the first time they thought like that, because previously it was mostly hard coded. Okay, but then it's like based on the samples that I see, can I update the weights and improve my prediction and so on. So I will make all this precise. So again, if you look into the eye also has more or less like structure like this. You have like multiple sensory inputs going on. There are multiple levels of processing going on, and maybe similar to CNN. Like there are like similarities. In fact, if you go to the original author YouTube, he has a couple of lectures just on this. Okay, so I strongly recommend that you go there. I don't need that much maybe right now. So there are also kind of like backward connections are also kind of seen and proposed also. So this could be perhaps an idea behind RNN, the feedback loop. Okay, so there were some initial models on that, which is interesting, because if I'm looking at a set of text and I have predicted a next word, this next word should go as an input in my model as well, compared to some of the previous words. So this is like going back. Okay, so output goes back as an input. Okay, so this is the feedback loop. So this could be used in text or sequential data, time series data, and so on. So this is important for us. Okay, this is where really concrete things happen. So this is the model. This is a perceptron. Okay, this is neuron perceptron. Okay, what is going on here? Here you have an input x1 to xn. This could be any input. Okay, it could be pixels and so on. Okay, so here what you see are the weights. Okay, and what we do is that these weights are multiplied with x1. This W2 is multiplied with it should be x2, I guess, and this multiplies with x3 and so on. Okay, so basically what we do is a linear combination of the input with the weights. Okay, W1 x1 plus W2 x2 plus W3 x3 plus Wn xn. So this is now some number. So this notation denotes that linear combination sum. Okay, and then there is a concept of a threshold, and this threshold is something you may set again by kind of writing it explicitly, and then you say that if this is above the threshold, so meaning if the linear combination is greater than t, if you can put the t on the right, then I will predict that it's 1. If it's less, then I will predict that it's 0. Okay, so this is a simple prediction function you have. Okay, so this is the prediction you have, W1 x1, sum of W1 x1, and compared to t, which is a threshold, you will predict, okay, whether the output should be, y is the output, right? So y is the output, and then you will say, okay, whether it's 1 or 0. Now depending on the problem, your threshold may change. Okay, threshold itself needs good understanding, but this is the basic perceptron model. And even threshold you may not need to do hard coding. So I will tell you precisely, just based on the loss function we can get away with explicit threshold. Okay, so when this was proposed, then the news was huge in 1958. It was even described as because already AI is becoming so huge that it is surpassing humans, and maybe at some point AI will go against AI, and Frankenstein means like someone who created it kills that. So you know who created. Okay, so humans created, so we don't know if AI will take over humans. And so there is a suggestion by Hinton that we are just one phase of the evolution. So we should not be too emotional that machines take over us, like we get annihilated because some better being in quotes took over someone. So maybe it's how things are going to be, more intelligent thing. Okay, we are emotional about that, but why should be, right? Someone better than us, useless, we will be useless. So if you look into perceptron, then why did they declare that this perceptron is Frankenstein? Well, in those days logic gates were there, okay, and logic gates basically are functionally complete. So which set of operators are functionally complete, right? So you have AND and OR are functionally complete, yes or no? AND or OR, can I build any circuit with AND or OR only? No, right? So AND or not? Yes. Okay. So they are functionally complete. So basically, or you can just take NOT or NAND. Sorry, not NOT. NAND, right? NAND. So basically, you can have NAND gate and you can construct any output that you desire. So the reason why perceptron was interesting, because they could look at this figure like that, and they can say, oh, look, this is like a perceptron. The input X that you give, Y that you give, I can design a weight and the threshold, and then I can behave. The perceptron will behave like a like an AND gate. Okay. So let us check that. If 1 1 AND gate is 1, right? So if I put 1 times 1 is 1, 1 times 1 is 1, and you have to plus it. So it's 2, and 2 is greater than or equal to 2, which is true in this case. So the output will be Y will be 1. Okay. So 1 times 1 plus 1 times 1, 2, and threshold was 2. So 2, actually in our case it should be equal, I guess, right? So because I want to predict 1, right? So I will change this a bit. I will just make it greater than equal, and that will work. So 2 greater than equal to 2, yes. Now you can try 1 0, right? So 1 times 1 is 1, and 0 times 1 is 0. So total is 1. 1 is greater than equal to 2? No. So its output is 0. So 1 0 was supposed to be 0, and it is indeed predicting that. So you can check all this, or also you can check. So the reason why they said that it's in those days, 1950, where there were no image segmentation, nothing. Okay, basically it was just a small perceptron. But the reason why they said it's important is because it can already behave like a like logic gates. And once it behaves like a logic gate, essentially they thought that now it can build anything. Okay, there were some. Obviously, there were further developments going on in this direction. So they said, okay, you can do AND, you can do NOT, you can do OR, and it is okay that it's functionally complete. But can one perceptron emulate XOR? Actually not. You can try that. Exclusive OR. Okay, exclusive OR behavior cannot be generated by a single perceptron. You can try anyhow to fix a weight. You have a full freedom to put these weights in question mark here and threshold. Whatever threshold you put, you will never be able to generate the behavior of an exclusive OR. So then there were some negative results by Minsky and Papert in 1960. They're saying, no, this is not for complicated logic gates and something. This perceptron is not good enough. Okay, but then why should we bother? Because even in digital circuits, we are not working with just one gate. We combine the gates to make more complicated outputs. So that essentially gave the idea that exclusive OR may not be described by one perceptron, but I can combine them. So if you combine 3 perceptrons, then it can behave like a XOR gate. Okay, so you can check this offline with this values explicitly of threshold and the weight values for XY inputs. It behaves like exclusive OR. So the idea behind is that from one perceptron you may look into combining these perceptrons, and it may give you some exciting outputs. Okay, and we can also extend from Boolean to reals. So why stick to Boolean inputs? So this was the next step of things. So excise that goes into input, this does not have to be Boolean 0 or 1 only. It should be any real value. So that was next step. And with this, another view of a perceptron is like it's like a hyperplane. Okay. So if you look at the equation Wi xi plus b, this is nothing but a hyperplane with the normal is given by the vector w. So essentially, classification problem of predicting whether given entry is 0 or 1 is like learning this hyperplane w1 x1 plus w2 x2 is equal to t. Okay, so if it is greater than equal to t, meaning it makes w makes an let's say an acute angle with this weight vector, it will classify as 1. If it makes obtuse vector angle, then it's classified zeros. Okay, something similar we see in SVMs as well. Okay, so basically this is the decision boundary, and so there is a nice geometric interpretation of a perceptron. Perceptrons are in the current form. If we look into this where t is fixed, then it is like a hyperplane. Okay, but may not be like a hyperplane. So it's like if I look into this form, then I'm thinking that the data is linearly classifiable. Okay, but this may not be possible that the data is linearly. Is possible to linearly classify a data. Okay, so we may need to make it a nonlinear, and if you use a sigmoid, then certainly it becomes a nonlinear model. Okay, so we have perceptron, and we extended the values to real values, and we have a geometric interpretation here that one perceptron behaves like one hyperplane. Now an intuition behind this is that now if I combine this perceptron, then it can learn complex structures. Like I may ask whether a point is inside a pentagon or outside. So if you see the pentagon, there are 5. It is defined by 5 intersection of 5 hyperplanes. Okay, so one hyperplane, one hyperplane, one hyperplane. So this gives you an intuition that I need 5 perceptrons to identify whether a point is inside or outside. Each perceptron will decide the point is on my correct side. Each perceptron will decide whether the point is on the correct side, and combined agreement on the correct position of the point which is inside the pentagon, let's say, if they match, then we say that the point is inside the pentagon or outside the pentagon. So things can be combined. As I said, one perceptron learning this point is above or below, another perceptron this boundary, another perceptron this boundary. So then you can make a perceptron now decide whether the point is inside pentagon or not. Okay, so basically by combining you get to learn complicated features. You get to learn even this. Now the question is, point is inside any of these pentagon. So you need a 5 perceptron to learn each of the hyperplanes. So 5, 1, 2, 3, 4, 5, and you need 5 for this guy as well. So 1, 2, 3, 4, 5. 5 perceptron. So this 5 perceptron will decide whether the point is inside. This 5 perceptron will decide whether the point is inside. And then the question was, it could be either here or here. So you do an AND of this. If the point is correctly on the correct side, meaning inside, above this, this side of this. So if they all match, you do an AND of that. All match, then this will be true. And if they decide the point is all inside, then this will be true. Okay, or one of them is true. It doesn't matter. Okay, because anyway you're taking OR. Of course the point will be in one of them only, it cannot be in both. So only one of them will be true, and you're taking an OR, then you can decide the point is anywhere inside. So basically, as you can see, you can make it more and more complicated, and you can learn very complex decision boundaries. Okay, nonlinear, it does not have to be now a linear separable problem. Okay, the one data set is completely inside the yellow region and the other data set is outside. So this is a nonlinear region now, defined by nonlinear decision boundary. Of course, it's a composed of many linear boundary, but it can it is not necessarily one linear hyperplane. Okay, so this is so now if I have to do a handwritten digit classification, then these pixels will be 784, so 32 by 32, I guess, right? So that will be a vector of 784 dimensions, and so given an image of 32 by 32, I make it a vector of dimension 784, and then this vector goes in the input layer. Okay, so this x1 is the first pixel, x2 is the second pixel, and so on, and it goes in, and then there are weights which will be learned via training process. Let us say you learn that weights during training process. So these weights are well known, so they got linear combination of these and then arrive here. So it's a multi-layer perceptron, right? Where one set of perceptron feeding output to the another layer of perceptron and so on, and then finally we do the prediction. So if it is 2, then it will give me the predicted value output 1 probability. No, I mean it will say that it's 2. Okay, so if there are like 0 to 9, then there are 10 classes, and the output will predict which of the classes. Or the problem could be binary, 2 or not 2. Okay, so in this case it may say 1 or 0 because the problem is focused on 2 or not 2. Okay, so that's okay. So now we more or less have an answer that what is in this black box, where voice signal goes in, transcription comes out, images goes in, text caption comes out, game state goes in, next game move comes out. There is this neural network power going on, driving most of the revolution of machine learning. Even the generative models that we will see relies heavily on neural networks. Okay, so one of the things is we have seen threshold T, and that T could be like hand crafted, but then also you may, as I said, you may get rid of that, and you may use some other activation functions which are some proper functions like 10h function, sigmoid function. Okay, so there are many possibilities of activation functions. So this symbol that you see here, sigma z, is a sigmoid function. Okay, so now the next step that you may be wondering is so we have these weights, right? So this is a parametric model, right? So the function is like this: the input goes in, it gets multiplied by the parameters w, so it gets a linear combination, but initially you don't know the w, right? So that's where the training will happen, because the data is given to you for each x. What could be the good output? That's the data I know. If I take an image of a 2, that I already know that it's 2. That's my sample. Okay, so this data I already have. This is the training data I call, and so this is the image and this is 2. So I will feed in. Initially these weights will be random because I don't know, and I will do the sigmoid activation and see what is the output. So did it predict 2? Okay, if it predicts 2, then maybe not much changes to the, even though initial weights are random, I may not want to touch or change too much. I will bring in another figure of 2 but written in a slightly different way, and then again it goes into this. Now this time if it does not predict that it's 2, then it's an error. Then these weights are not good enough. It recognized the first 2, but if I wrote slightly differently, it did not recognize. So this means that I will make a loss function. So what I predicted and what was the actual output, I can take a difference. So that becomes a loss function for me. Okay. So then I want to minimize this loss. So it's an optimization problem. Minimize the loss over the weights. Okay, because it's a loss. My output, what was the reference output, I want to minimize that. So I may do this for many samples. For some sample it's okay, some sample not, but I can do a cumulative loss. Okay, I may want to do a cumulative loss. So my overall loss will be first image of 2 prediction loss, second image of 2 prediction loss. I sum all this loss. Okay, so I can sum all these losses, and overall my goal is to minimize the loss over the weight. So this is nothing but an optimization problem. So when I am dealing, so you may wonder why I wrote all this, right? This is nothing but it is used in the optimization process. This is called backpropagation. Okay, so one of the challenges in neural network was to actually learn this these weights. Training process was cumbersome, especially if you look into multi-layer perceptron. Once I build a loss function, it's an optimization problem, and I have to minimize with respect to the weights, right? Now if I have this chain of function, like this is like some weights and then activation function f, and then it goes into some other weights, right? Like here, right? It's a multi-layer perceptron. So it's a complicated nested function that we are going to do. Now if I have a loss function and that loss function involves this complicated function inside, and I'm supposed to do an optimization problem, I want to supposed to minimize the loss. Now I'm supposed to take the gradient. The first step in optimization method is to take gradient at equal to 0. Now how you are going to do the gradient of such a complicated nested function? Okay, that was a major breakthrough, and it was a major breakthrough because in those days computing power was not that great. So computing a gradient was very time consuming, and basically if you go and do it by hand, compute the gradients explicitly, it's way more complicated. So one of the greatest idea you can think of was using so-called chain rule, and of course chain rule itself is not a big deal. What is a big deal is to use the intermediate values in the chain rule. That is the big deal. So how can I use that, right? So let us say I have input that goes to the weights and it produces some intermediate values z. This is some intermediate value z. This is some numerical value. I know that value z. Okay, so that numerical value is there, and then from z to y I know what is the relationship. This is via sigmoid, so I know how to take derivative of y with z. Remember, when you do optimization problem, you are minimizing the loss with respect to the weights. So overall this loss function needs to be taken gradient with respect to the weights. So you have to reach here. So can you use chain rule starting from y, using intermediate values, and then ultimately going up to the weights? Okay, so this was interesting. This is just a single perceptron. So here, so chain rule, I have to go up to w, right? So dy by dw. Okay, the output whatever I have, because output it subtracted with the desired output. Desired output has no weights, right? Desired output is like the level, is a fixed number. So only y depends on z, z depends on w. So I will look for derivative of y, how to take derivative of y with w. Okay, so if I look into derivative of y with w, then y is sigma of sorry, not w, z. Okay, so of course I have to go there, but I want to do it by chain rule. So in the chain rule I see 3 variables in the chain. Okay, w, z, y. I have to go up to w. Okay, y is a function of w. So what I am looking for is dy by dw, and of course there are many w's. So let us say some ith w. Then this will be, I have to go back, right? So to get to wi somewhere here, then I have to do dy by dz. So dy by dz and dz by dw. Okay, so dy by dz, I know dy by dz because y is sigma of z. So dy by dz is sigma prime z, and dz by dw because z is a x1 w1 plus x2 w2 plus x3 w3 so on. So z is x1 w1 plus dot 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 plus xn wn, and somewhere there is xi wi. I am looking for dz by dwi. Okay, so dz by dwi. So all other w will be like a constant. So dz by dwi, partial derivative by wi, will be just xi. So you see that xi there, and dy by dz was sigma prime z. So this is your derivative with w. and this is what I will need in the loss when I'm optimizing. I will be needing this dy by dw, and I will use gradient descent. W is w minus loss, derivative of the loss with w, but derivative loss with w will boil down to derivative of y with wi. Okay, and I have to do this because loss will be a function of all the wi, so it will be gradient of dimension as big as the weights. Okay, one of them is bias, but again this is still a variable here. Bias comes with bias is like an offset that you are going to provide. You don't want your linear classifier to go necessarily passing to the origin. It's like ax plus b. This is your b term, the offset that you allow it to move around a little bit. Okay, so this is so how will I compute in practice? I did a forward pass. I had data that went in. W was random initially. Okay, so W was random initially. I got some z with that. So now I know the z, I know the sigma function. Derivative of that I know. I can compute sigma prime z, and I also know the xi because xi was the ith pixel, okay, or the component, okay, so of the input. So this value I know. Now I can use this value in gradient descent. In gradient descent I will be doing our updates like w. So I write this in vector form. W is w minus get w loss, but in the loss it will be like let us say L is the level, right? So it will be let us say some squared loss we are using. Then we are kind of w is dependent only here. Okay, so y is a function of w. So basically this will not play much role. Inside this gradient you will be needing an access to grad w y, and this is what we have. The ith component of grad w y will be dy by dwy. So you have this, and you may plug in these values and you update the weight vectors. That's your gradient descent, and you keep doing this. It's not like just one time you did and you're okay. No, you have to now bring in another sample. Okay, and if the prediction was bad, this gradient will be some significant value. Okay, because the loss is high. If the loss is high, then derivative with respect to w must be significant. Then it will be some significant quantity that gets the weights updated. So if my input and my weight vectors were such that the output was exactly the same as the label, then this y minus L, the difference, it will be 0, right? Because the loss is 0 for that sample, although the w was random. So but in that case you will see that the gradient is 0 and there will be no update to the weights. So it's a very clever design. If the loss is big, obviously the gradient with respect to w will be something significant, and this allows you to change the weights. Okay, and this change of weight necessarily improves your weight. Okay, because it's going to the minima, the weight that is giving me minima of the loss. That's the whole idea about the optimization problem here. So I will so if it was good, it's okay. Weights didn't get updated, prediction was perfect, but there will be some samples where the weights where the prediction won't be good, because random weights are very unlikely to be already good, right? So there will be many samples for which the output will not match with the loss. The gradient will be significant, the weights will get updated, and there will be a time when it will learn. Okay, the weights will be tuned in a way that it will be good enough, and then someone will give you a new set of images, and then someone will give you a new set of images, and then it will learn to predict that whether the image is a 2 or not. So one of the breakthrough, so now you can do this back propagation. I have a small set of slides for the next class. I will go to deep learning. I haven't gone to deep learning yet. We have neurons and MLPs, but we have some terms to define. So I will go. I will describe the back propagation in slightly more detail when you have multiple layers. But this is more or less the idea. It's all about maths now. It's like when I have multiple layers involved, how will you apply the chain rule to compute derivative with any weights, and not just weights here, there will be weights in multiple layers, right? So if you see multi-layer perceptron, weights are here also. So you have to compute derivative with respect to this. So then you go one step in the chain rule to compute derivative with this. So you have to go step by step, here to here, because this data is known. Remember the previous JAD, right? That JAD is useful. So this is the intermediate JAD that you found during forward pass. So this JAD you save it. All this intermediate data that you see, that when you pass an image and you got these intermediate values, that needs to be saved. Okay, because that is used in the back propagation later on. So that is the whole idea. Okay, you don't want to do explicit derivatives. You want to do chain rule and use intermediate values. So this is the idea behind the back propagation that we will see a little bit although that's not really needed for our case, but just for a bit of clarity for the deep neural networks. Okay, so this is more or less how multi-layer perceptron looks like. Okay, so these are the like outputs and weight notations that we may use. So you can see sometimes we may put superscript 2. So this is like 1 1, the first neuron of the second layer connected to first neuron of yeah. So basically these are the weights. So what I'm saying is these weights which connect yeah, basically these are the second layer weights. So that's why it's 2, and this is connecting neuron 1 to 1. So first neuron of this layer adds with first neuron of the next layer, second neuron of this layer of the second layer, second neuron of the second layer, okay, and this is connected to the first neuron of the next layer. So that's why you see 1 to 1, 2 to 1. Okay, similarly you can think of these weights also. Okay, 1 to 1, okay, 2 to 1, 3 to 1, 4 to 1. So these are just the notations, okay, that we have, and this is how the operations look like. There is always one extra weight that we write, and these are called bias. Okay, so and we put this like every layer. Okay, there is a one bias term here, one bias term here. Okay, so as I said, I will wrap up now for this initial part, perceptron and basic idea of perceptron, forward computations, and how the weights are updated. Okay, and I will take 15 minutes in the next class and then describe deeper variant of this. So basically these are the set of samples you have. X1 the output is known, Y2 X2 output is known. You build a loss function by summing this individual losses. This loss could be very simple as this, but then there are many types of loss. If it's a classification loss, then we use some specific type of losses. We will see that. So we build a loss function over the samples I, and then we take derivative with the weights W. These weights W may be distributed in everywhere in the layer. Okay, we have to reach there via chain rule using the intermediate values. So that's more or less the wrap up of the neural networks, and we will do deep neural networks in the next class.